So I hope this screen is visible uh, in PPT mode, where we are having this Bell's method for design of shell and tube heat exchanger.
Ma'am.
Is it visible?
Yes, ma'am.
Right. So very good morning to all of you. In today's class, we will discuss Bell's method, but before discussing this, let me revise the last class. In the last class, we have mainly focused on design of shell and tube heat exchanger using Kern's method with one example. We have solved the example in detail when only initial parameters are known to us. So I believe that method is approach is clear to you. And next we have started the Bell's method. So when we consider this Bell's method, uh, by now you understand that whatever method we are considering, that is related to design of only shell side of shell and tube heat exchanger. Tube side design will remain same. Okay, so when we consider this Bell's method, uh, it basically developed over Kern's method, so it addressed some of the limitations of Kern's method. So if you consider Kern's method, it only counts the cross flow zone, and that too at the middle. Okay, that too at the center only. Okay. However, this Bell's method counts other streams also. In the last class, we have discussed those streams, and like we have cross flow streams, we have uh, stream A and E, which are leakage streams, and bypass streams we have, and uh, along with that we have another stream, that is stream F, which is corresponding to pass partition plate, and that is in shell side, not in tube side, right? So all these streams we will count in Bell's method except F. Okay, stream F, Bell's method does not count stream F. So what we can say that it addresses the uh, limitation of Kern's method, and gives more practical design. Okay, considering many parameters. Okay, so when we consider the Bell's method, um, what we do basically, first of all we will see the shell side heat transfer coefficient, and then we will see shell side pressure drop. Okay, and when we consider this either shell side heat transfer coefficient or pressure drop, we basically consider the initial, or we can say the uh, basic parameter, or we can say the ideal parameters, and then over that we will consider the correction factors based on different streams, right? So this practice we will consider in Bell's method. So first of all we will focus on heat transfer coefficient, and this heat transfer coefficient, if you see, for shell side, it includes many parameters. Okay, so the first parameter I am having is HOC, FN, FW, FB, FL. HOC, when we are considering, this is heat transfer coefficient calculated for cross flow over an ideal tube bank where no leakage and no bypassing occur. Okay, so the point is, when we consider this HOC, this is about the heat transfer coefficient, and this is for cross flow. Okay, but if you see the cross flow in Kern's method, okay, cross flow in Kern's method, so it only counts the middle part, right? However, when we consider this cross flow, it considers the ideal tube. Okay, it means that it also counts the middle part only. Okay, where different tubes are available. Okay, but it does not have any other effect, like any baffle is not there, any other tubes are not available in cross flow. Okay, so this is basically the ideal case. Okay, how we will consider that, and the related factor for this shell side heat transfer coefficient, that we will see. Okay, but I hope this you understand. This is the ideal case where only tube bank is available, where I am not considering any effect or what we can say, any hindrance from any other stream. Okay, even cross flow stream effect is not available over here. It is the ideal tube bank. Okay, so this is HOC. How we will calculate that we will see. And other factors we are having, like correction factor. So this Fn is the correction factor of number of vertical tube rows. So this Fn, if you consider, in short we call that as the effect of cross flow, though this is cross flow only, HOC. Okay, but this is the ideal tube bank. Here we will consider the effect of other tubes available in what we can say, cross flow zone. So Fn is related to cross flow zone only. Consider FW, this is window effect correction factor. If we will see in subsequent slides that what is the cross flow zone, little bit we have already discussed. Okay, but we will see with respect to computation. So what is cross flow, what is window zone and all. And other correction factor we have is the bypass stream correction factor. Okay, we have the bypass stream which is available in the clearance section, clearance area. So that we will see how to count this. Okay, and lastly we have the correction factor based on leakage. Okay, and you understand leakage when we consider this is for baffle to tube space and baffle to shell space. Stream B, sorry, stream A and stream E we consider in leakage correction factor. You can recall the last class. Okay, so in that way we can consider different correction factors over HOC. So first of all we will see the HOC, but before that the important guideline is that total correction factor. Correction factor total means the multiplication of Fn to FL. Okay, if you consider this particular correction factors, the correction factor vary from 0.6 for poorly designed exchanger with large clearances to 0.9 for a well designed exchanger. Okay, so we need to keep all these parameters towards 0.9. Okay, so in that way we will consider this. So let's start with HOC and how to count other parameters. So when we consider this HOC, ideal cross flow coefficient, when we consider this what we can say, Kern's method. Kern's method, in that case we also consider the cross flow area, but that is the maximum cross flow area. Okay, based on that AS you have calculated this US. Okay, so same thing you need to do over here. The only difference is when we are calculating Reynolds number, here we will count OD of the tube. Like fluid is flowing over the tube, that is this HOC is that ideal. I hope you are getting my point. However, when we consider the Kern's method, Reynolds number counts DE, equivalent dia. If you recall the Kern's method, so this was equivalent dia, and here this is OD of the tube. Considering that what we can say, fluid is flowing over the tube, okay, without any hindrance. Okay, that's why DO we consider over here. So Reynolds number we can calculate. Once we have the Reynolds number, we can calculate heat transfer coefficient based on this. Nusselt number is a function of Reynolds number and Prandtl number. This is the same expression, but here you need to consider DO instead of DE. Okay, so this H, JH, that is heat transfer factor, when we consider this is, you can use this graph to find out this JH, okay, depending upon the Reynolds number. Okay, so each type of problem has that respective graph to see the value of the correct value of the factors, so that you can see. Now once I'm having HOC, that you understood, I hope you have understood that we consider DO, OD of the tube. It means tube, it is the ideal tube bank. No hindrance we have considered so far. Okay, so fluid is flowing over the tube smoothly, that you can see, that you can understand only. Now we will see all these correction factor one by one. First of all, we have FN, that is tube row correction factor. Okay, so tube row correction factor, it is denoted by FN. So it is basically count the cross flow zone. Okay, complete cross flow zone. Okay, so it depends on number of tubes crossed. Okay, so what does it mean, that we will discuss. What is the cross flow, and what is the meaning of number of tubes crossed. Okay, so when we consider the Reynolds number, okay, because it depends on the flow, so Reynolds number, if it is more than 2000, we consider turbulent, and Fn should be taken from this graph. Okay, so Reynolds number for turbulent zone, this is for greater than 2000. Okay, so however we have discussed that in shell side, turbulent, or we can say turbulent is achieved in what we can say very less Reynolds number, like more than 200 or so. Okay, but here we are considering the complete turbulent, fully developed turbulent flow. Okay, so if this is the case, Fn you can find from this graph. Please discuss if you have any confusion. Okay, and here I am having this NCV, and depending upon this NCV we need to find this Fn. Okay, and this NCV, when we are considering, NCV is the number of restrictions crossed. Okay, number of restrictions crossed, and if you see what is written over here, number of tubes crossed. Okay, so number of restriction, either we say, or we can say number of tube crossed, or we can say number of tube rows crossed. Okay, this is the same thing. Okay, so NCV is the number of restriction crossed. Restrictions, how we can define restrictions in terms of tube rows. Okay, tube rows, how many tube rows are available between baffle to baffle tip. Okay, cross flow zone, if we ask you what is the cross flow zone, in the last class we have discussed that between two consecutive baffle tips, whatever zone is available where I am having the tube and shell side flow in cross, or we can say they are crossing each other, so that zone we consider as cross flow, which fall between baffle to baffle tips. Okay, so this NCV is only the number. Okay, you need to calculate this number, and this number of tube row crossed or tube rows are available between baffle tips, and that is NCV, and correspondingly you can see the value of Fn. Now the question is how to find this NCV. Okay, but before this, let me discuss that what is NCV. Okay, I hope from this schematic you will understand better. Okay, so if I consider the complete what we can say shell side. Okay, shell side, So cross flow zone will occur between two baffle tips. Okay, and every time either you go this way or you go this way, every zone will have same cross flow, right? Because we consider that segmental baffle cut of same in all baffles. Okay, so this cross flow zone will available from here to here. Okay, in between fluid will be fluid flow of shell and tube will be cross each other. Okay, and this is the baffle tip, and between baffle tip to shell, this is the window zone. Okay, this is the window zone. Okay, now NCV is the number of restriction crossed or number of tube rows between baffle tips. So this is the what we can say side view. Okay, side view, if you are seeing from exchanger, it looks like this. Okay, however, if you consider, if you see the cross sectional view, somewhere it will look like this. Okay, this is one baffle. Okay, one baffle will be like this, where only this section will be removed. Another baffle will have only this section will be removed. So this is the cross flow zone. Okay, NCV will be this number 1 2 3 4 5 6. In this case NCV is 6. Okay, that is the number of tube rows between baffle tips. Okay, and when we consider the HOC, that is at the what we can say ideal tube bank, where it is not affected by any other tube. Okay, so in that case you may consider this one HOC, or this tube for HOC, this tube of HOC, whatever, but it is not what we can say, it is not uh, affected by other tube rows. Okay, so if you consider this tube row, when the fluid is falling over this, it will be distributed in two, and then this tube will come, and then this tube will come. So obviously when the HOC, when we are considering for ideal tube, you can imagine that as I'm having only a single tube. Okay, where no restriction we are considering. Okay, so in that case, when fluid is flowing over these tubes, obviously it will hinder the what we can say the flow over the ideal tube. Okay, so to count this, we need to consider this NCV. Okay, NCV you can consider, you can calculate like this. Okay, here I am only I have only shown this circles to let you know, to make you understand the NCV. However, for actual system we need to calculate this NCV. Okay, using this expression. So when we consider this NCV, this is equal to dB minus 2 HB by PT dash. Okay, just 1 minute. Okay, so when we consider this cross-sectional view, let me discuss the parameters involved over here. This is the shell diameter. Okay, that is denoted as DS. Sorry. So this is shell diameter. Inside this we have bundle diameter. Okay, dB is the bundle diameter and ds is the shell diameter. Okay, and if you consider hb is this height. Okay, and if I consider this particular section, this is nothing but the baffle. Okay, this theta b is the angle which is making by this arc at the center. This chord, sorry, not arc, this chord, whatever angle it is making at the center, that's theta b. Okay, and this HC we consider based on this height, right? So NCB is basically when I'm having bundle diameter. If you consider this particular expression, this is nothing but here I'm having bundle diameter minus 2HB, okay, bundle diameter, and whatever section of bundle diameter is available in window zone, okay, cross flow zone you understand, like this and this, in between whatever zone is there, that is cross flow zone. This section and this section is nothing but the window zone, okay. So whatever part of the bundle is available in window zone, that we need to deduct. Twice of that we need to deduct, because HB will be here, and if I consider second baffle over here, HB will appear over here as well, right? So dB minus 2HB by PT dash, okay. So dB minus 2HB, we have considered this distance from here to here, dB minus 2HB, okay, by PT dash. PT dash is basically, PT dash is this distance, that is pitch, uh, that is tube pitch, okay. But here usually we define pitch as PT, but here I am representing PT prime, PT dash, okay, PT dash or PT prime. In that case, if I am having like square pitch, okay, PT dash will be equal to PT, because this distance between these center to center of two consecutive tubes will be equal to PT only, and that is PT dash also in case of case of square pitch. However, in case of triangular pitch, when I am considering, this height will be slightly lesser than PT, okay. So in that case, PT prime will be equal to 0.87 into PT, okay, that you need to consider, okay. So in that case, we have to first of all find HB, and then we will deduct twice of HB from this bundle dia, okay. And in that case, HB, when I am considering, that is uh, denoted by dB by 2. dB by 2 means half of bundle dia, means this height. Between this, sorry, between sorry, this height is HB, sorry, this height is dB by 2, sorry, this height is dB by 2, okay. uh, minus ds means shell dia, 0.5 means half of shell dia, okay, which is this one, okay, minus bc is basically this minus bc is this, okay, that is BC, or we can say the baffle cut usually like 0.25 or so in BC. When we are defining, that is basically HC by DS, okay. So that is baffle cut, and 0.5 into DS, half of DS, okay. So this height minus this height, so it will give me this height, okay. Finally I draw the straight line, okay. So this uh, this complete expression will give me this height, okay, and dB by 2, this height minus this height, it will give me HB, okay. So that in that way we can find this HB. So twice of HB you need to deduct from here, or you can simply consider geometry, okay. You people are very good in geometry and mathematics, I believe. So in that way you can consider geometry, you can apply geometry and find out HB, okay. So NCB would be equal to dB minus 2HB by PT dash, Okay, and this PT dash or prime, whatever you say, is the vertical tube pitch equal to PT for square pitch, or 0.87 into PT for triangular pitch. Okay, so in that way you can consider, you can calculate NCV, and this NCV value should always be what we can say, complete number, because this is number of tube rows na, which will never be decimal. Okay, so that you can consider NCV as complete number. Okay, so whatever you obtain, you need to consider that NCV, either round up or round off. Okay, so in that way you can count. What you need to consider, that we will discuss while doing the example. So NCV you can calculate like this, and NCV, when you have calculated, after that you can use NCV over here to find out FN, right? Okay, so that is for Reynolds number more than 2000. If Reynolds number is between 100 and 2000, we have transition zone where Fn should be 1 only. Reynolds number less than 1, we have laminar zone in which Fn is a function. Fn is proportional to Nc prime my power minus 0.18, and Nc is the number of rows crossed in series from end to end of the shell and depend on the number of baffles. Okay, so how many cross flow zones will be available into NCV? That would be NC prime. Okay, so in that way you can consider FN, that is tube row correction factor. Okay, if you have any confusion, please discuss. Okay, I don't understand whether you people are getting or not, because no one asked anything. Okay, and after completing this I will give the tutorial for or problem to solve for Kern's method as well as Bell's method, and probably in that while solving that you will face some issue or some doubts like that, so we may discuss then. Okay, so FW is the next correction factor, which is window correction factor. And when we consider this window correction factor is applied for effect of flow through baffle window zone. Okay, window zone, when we consider, I hope you understand, we have discussed that window zone is this. Okay, this zone, this zone, or this zone, or this zone, like that we can consider window zone. So, window correction factor is applied for effect of flow through baffle window zone. Okay, between baffle tip to shell. Okay, it is a function of heat transfer area in window zone and total heat transfer area. Uh, Actually, when we consider this hmm, window zone, okay, this FW depends on this RW. Okay, RW, once you know, you can see FW directly, but how to find this RW? RW will depend on, or we can say it is the ratio of number of tubes in window zone to total number in, so total number of tubes in baffle, sorry, in bundle. What does it mean? Mm, so please see this uh, image or this schematic. If I fill this complete uh, cross flow zone, or let me tell you in different way, if I uh, or it is better to understand from this, just give me 1 minute, let me erase this. what I'm trying to emphasize, if you consider this bundle section, okay, which is in the window zone, so RW basically counts the number of tubes in this window zone, okay, divide by total number of tubes in this uh, bundle, okay, number of tubes in window zone divide by total number of tubes in bundle, okay. In other way, how we can consider this, it will be like area of tube, sorry, please try and understand, it will be uh, proportional to, or we can relate that number with the heat transfer area available in bundle zone, available in window zone, divided by total heat transfer area, okay. In other way, let me be more specific, the area of bundle, okay, area of bundle available in window zone by total bundle cross sectional area. It means this area divided by total bundle area. Fine. So please, now you see this RW is the ratio of number of tubes in window zone to total number in the tube in the bundle, okay, which will depend on the areas, okay. Sectional area of bundle in window zone by total sectional area, cross sectional area of bundle. I hope you are getting my point. So we need to calculate first of all RW to find out FW. RW will be 2NW by NT. 2NW because when we consider the this correction factors, these we are considering uh, in zone wise. Okay, so like cross flow zone, when we are considering cross flow zone between two baffle tips. Okay, so in that region window zone will be twice, two window zones, okay. So 2 into NW by NT. NW is number of tubes of bundle in window zone by total number of tubes in bundle. So NW would be NT into RA, okay. Now this NW you can find out by NT into RA prime, sorry, not RA, RA prime. NT is the number of tubes, total number of tube in the bundle. RA prime is what? RA prime, as we have discussed, it depends on the area. RA prime is the ratio of bundle cross sectional area in window zone to total bundle cross sectional area, okay. Bundle cross sectional area in window zone by total bundle cross sectional area, okay. So that is basically RA prime. And if you see here another parameter I am having, which is RA, okay. RA is the window area by total area, okay. So RA prime is also area in window zone uh, by total area, okay. RA is also window area by total area. So what is the difference? Okay, because value cannot be same, na, otherwise only one parameter we could use, okay. But here I am having two different parameters. The difference between RA and RA prime, if you focus on this RA, this is window area by total area, okay. It depends on the shell dia, please keep in mind, okay. Window area in complete bundle, sorry, window area in complete shell by shell cross sectional area. I hope you are getting my point. Window area in complete shell by total cross sectional area of the shell, okay. RA prime is the cross sectional area of bundle in window zone by total bundle cross sectional area. The point to consider over here is RA dash, when I am considering, it will depend on the bundle cut, okay. RA, when we are considering, it depends on the baffle cut, okay. Let me I'll try to make you understand what I mean. Like when we considering RA prime will depend on bundle cut, and bundle cut would be HB by DB, right? HB by DB will be the bundle cut. Fine. And when we consider RA will depend on the baffle cut, which will be HC by DS. Baffle cut is HC by DS. Bundle cut is HB by DB. Okay, please keep that in mind. So whatever you need in that, here I am considering RA prime. Wherever we will consider RA, that we will see. So you need to consider the x-axis which is cut. Okay, whatever cut you need to consider. Okay, so RA prime, for that we will consider HB by DB, that is the bundle cut, and whatever value is there, you can use the upper graph. If you see the arrow, okay, upper graph will be for this axis and this axis. Okay, lower graph will be for this axis and for this axis. Okay, so from this you can see the value of theta b, which is available over here, but here we only need RA prime. So bundle cut you need to calculate first, then you need to see RA prime. Once you know the RA prime, you can calculate NW, and NW, once you know, you can calculate RW, and once you know RW, you can find out FW. That is window correction factor. I hope you are able to follow what I am trying to convey. So here NC I am having, NC is then equal to NT minus 2 NW. So now NC is the total number of tubes in cross flow zone, right? Another parameter I am having is the bypass correction factor. Okay. So bypass correction factor, if you see, we need to consider stream C over here. That is the only stream available in the complete bundle as bypass stream. Others are what we can say leakage streams. Okay. So FB is the bypass correction factor. So this factor corrects for the main bypass stream, the flow between tube bundle and shell wall, and is the function of shell to bundle clearance. So if I'm having the more clearance, more there are chances to accumulation, or we can say the accumulation of more liquid available in that clearance, and which will be considered as dead zone. Okay, so we need to disperse the liquid while accumulating in clearance. Okay, and that we do through sealing strips. Okay, so we will see what are the sealing strips. So if you consider this particular image, okay, here I am having the bundle diameter, and in between different tubes are there, and if you see this vertical section, okay, this strip, all these strips we consider as sealing strips. If you see from the side, it is nothing but the what we can say rectangular metal sheets, metal strips which are welded between baffle to baffle. Okay, so what it does basically, when I'm considering this sealing strips, these are placed vertically, okay, and these are welded between two baffles. Okay, so what it does, it it reduces the area which is available for liquid to accumulate, or we can say that because of this sealing strips, uh, the what we can say, the liquid will get dispersed. Okay, which is available here as well, which is available here as well. So because of this, these strips, when fluid will come in contact with these strips, because these strips put the hindrance in the flow, it will not allow liquid to accumulate. It disperse the liquid immediately when the liquid comes over here. Okay, similarly this zone. Okay, however, when we consider this particular section or this particular section, though clearance is also there, but sealing strips we are not using, because this fluid or this section will fall under cross flow. Okay, so whatever sinusoidal movement will be there in shell side, cross flow zone is the zone where dead zone is least possible. Okay, because of the fluid will come over this, so it will dispersion of the fluid will be, or movement of the fluid will be easier over here in comparison to clearance at the top and bottom. Okay, so these are the sealing strips, and photograph, if you would like to see, this is the actual heat exchanger. These are the number of tubes, and you consider these are basically the sealing strip. These are welded between baffle. Okay, between two baffle, you can see over here. Okay, and this we consider for the heat exchangers which are of pull through type or internal floating head. Okay, so if internal floating head is there, you need to put the sealing strips, uh, what we can say, you have to put the sealing strips, otherwise the without sealing strips also it will work, but that condition you need to check. So next I'm having is FB, that is bypass correction factor, and which can be calculated by this particular expression. I hope you have the idea that what are the sealing strips and all. Okay, and why we need to put that sealing strips. Okay, so FB is the factor which counts the effect of that what we can say, sealing strips, or it gives the bypass correction factor. Okay, all these parameters you can see. Alpha we have 1.5 for laminar flow, for depending upon the Reynolds number you can see the alpha value. AB is the clearance area between bundle and shell. Okay, so bundle and shell, so AB would be this much. If you see between two baffle, this is or we can see like this is also the sealing strip. Okay, so we can consider this area or this area as the AB. Okay, between baffle and between bundle and shell. Okay, AS is the maximum cross flow area, as we have counted in Kern's method. NS is the number of sealing strips. Yes, that is important parameter. Number of sealing strips and counted by bypass stream in cross flow zone. It means the number of streams, number of sealing strips, sorry, number of sealing strips, depending upon the number of sealing strip we can have FB value. Okay, so how to consider correct number of sealing strips, that we will discuss. Okay, NCV is the number of restrictions in cross flow zone, that we have already discussed previously in FN correction factor. So the condition is NS should always be less than or equal to NCV by 2. Okay, if let's say if NCV is 12, NS should not be more than 6. Okay, so like that you can put the NS value. However, how to choose this correct NS value, that we will discuss when solving the example. Now if I keep on telling this, no, you will not understand that how this will be counted, so that I will tell you with the help of example. Okay, so NS we need to fix so that we can fix FB. Okay, and when we consider this FB, that is bypass correction factor, AB is this. AB is this, which depends on the LB, that is baffle spacing, into clearance, that is DS minus DB. Okay, so this and this area will be counted as AB. Okay, I'm having another condition that if no sealing strip is required. Okay, what does it mean? First of all, we need to check whether sealing strips are required or not. Okay, so first of all, you need to require whether sealing strips. Sorry, somebody has come. So, okay, let me tell you in that way. First of all, we need to check whether sealing strips are required or not, and if sealing strips will be required, we will use this expression, and if it is not required, we will use this graph to see the value of FB. Okay, so the point is how to check whether sealing strips are required or not. Okay, that I will again discuss with the help of example. Okay, there are so many other things which we need to consider in this FB correction factor, so that it will be good if we discuss that through the example. Okay, so here I'm having bypass correction factor. Another correction factor I'm having is the leakage correction factor. Leakage correction factor, as you know already, here I am considering stream A like this and stream E. Okay, both of these streams we are considering over here. So this factor corrects for the leakage through tube to baffle clearance and tube to shell clearance, tube to baffle and tube to shell clearance, right? So we will discuss that for these two streams. Correction factor is FL, which depends on this beta L, which is the factor, and ATB, and it will depend on ASB and AL. Okay, beta L is the factor, ATB is the tube to baffle clearance area, ASB is the shell to baffle clearance area. Okay. ATB is the tube to baffle clearance area. Tube to baffle clearance area means this one. Okay, ASB is the shell to baffle clearance area, means string E. Okay, addition of this will give AL. Okay, now if I consider this, how to find this ATB, if you see this ATB, this is nothing but the gap between hole in baffle and tube OD. Okay, so in this is basically ATB, and it is calculated like CT into pi d naught. CT is the what we can say, this gap. Okay, gap between what? Gap between baffle hole, okay, and OD by 2, right? So CT is what? CT is the baffle to tube clearance divided by 2. Okay, pi d naught. Pi d naught, if you can consider, that is the outer periphery into CT. So it will give the length. I hope you are getting my point. It will give the uh, pi d naught will give the length, and CT would be this distance. So this what we can say, multiplication will give the total what we can say, clearance area. Okay, okay. So this CT, or why we are considering this two? Because this CT is the clearance between tube to baffle. Okay, I think I have told you CT is the baffle to tube clearance by 2. Okay, but CT is the baffle to tube clearance only. By 2 we have already divided over here. Okay, so that would be the area of one this clearance. Okay, into NT minus NW. Okay, NT minus NW means this NT is the total number of tubes in the bundle minus NW, number of tubes in window zone, right? So the it means the total number of tubes which are inserted in the baffle. I hope you are getting my point. So in this way we can calculate ATB, and CT value will always be 0.8 mm. Okay, CT value will always be 0.8 mm. Next, I am having ASB, shell to baffle clearance. Shell to baffle clearance, when I am considering, this is E, this considered string E, so that is CS ds by 2. Okay, CS is the, okay, let me first discuss this ds. Ds is the shell dia, you know already, 2 pi minus theta b. 2 pi minus theta b means what? The baffle periphery. I hope you are getting my point. Just 1 minute. Okay. Okay, so 2 pi minus theta b. So it means we are counting this distance or this periphery. Fine. 2 pi minus theta b into ds is again the length of the periphery of the baffle, right, into CS by 2. CS is the baffle to shell clearance. Okay, CS by 2. And CS value you can see, see this standard table which is available in volume 6. Shell dia I am having ds into baffle diameter. So pipe shell, when I'm so here I am considering two shell, one is pipe shell, another is plate shell. Okay, pipe shell, where ready-made pipes are available which we can use as a shell. Plate shell, like I'm having the metal plate, by rolling it we can prepare the shell. Okay, I have discussed that before. Okay, uh, when we have discussed shell dimensions, um, yes. So here you can see that I'm having the range of shell diameter, and if you see here I'm having baffle diameter, that is ds minus this 1 by 16 inches. So in the bracket, or all these value if you are considering, these are nothing but the CS. Okay, so if your shell diameter will lie between this range, and it lie in both pipe as well as shell. So if you are given the range in plate as well as pipe both, you need to choose the pipe shell because that is already available, making what we can say, making shell is costlier in comparison to pipes. Okay, so the if diameter permits you, you should choose you should choose pipe shell instead of plate shell. Okay, so accordingly, depending upon the shell dia, you can calculate CS, you can see CS value from this, and then you can see ASB. So once I am having this ASB, we can consider this factor, and AL we can calculate, and beta L we can see from this graph depending upon AL by AS. Once I know beta L, we can find out FL, leakage correction factor. Okay, so in that way we can have all correction factors depending upon the heat transfer coefficient, that is FN, FW, FB and FL. Okay. I will continue after 2 minutes for this pressure drop. Okay, just give me 2 minutes. So I'm sorry for the delay. Actually, somebody has come to my office. So so we were discussing about different correction factors to find out shell side heat transfer coefficient using Bell's method. So that we have discussed, and now we will focus on pressure drop uh, in shell side using Bell's method. Okay. Now, when we consider the pressure drop, you understand that pressure drop, how we count the pressure drop, that is nothing but the friction loss. Okay, and friction loss, when we consider in shell side, it depends on different zones. As we have already seen that there are two zones, cross flow zone and window zone, and apart from this we have another zone that we call as end zone. Okay, from where the fluid is entering in the shell side. Okay, so that you can consider that pressure drop in cross flow and window zone, uh, we need to define, and we will sum them up to uh, have total pressure drop in the shell. Okay, so how many cross flow zones will be available, how many window zones will be available, how many end zones will be available. Based on that, we will calculate the pressure drop of each zone, and then that will be multiplied by number of zones to calculate the shell side pressure drop. Okay, I hope you understand. First of all, we will focus on the cross flow zone pressure drop. Cross flow zone between baffle to baffle tips, that you already aware of. And uh, when we consider this pressure drop, as we have discussed in heat transfer coefficient, that we will consider the ideal case first, and then the that correction factor will be counted over that. Okay, so same thing will happen over here. Like I'm having this delta PC pressure drop in cross flow zone between baffle tip, and here delta PI is the ideal pressure drop, uh, we can say, for ideal tube bank, or pressure drop for ideal tube bank, and that would be corrected by FB, that is bypass correction factor and leakage correction factor, because it is between cross flow zone. Okay, so in cross flow zone, if I consider friction loss, that would be counted uh, like for leakage stream, like baffle to what we can say tube gap, and that what we can say baffle to shell clearance. Okay, shell gap. Okay, so leakage correction factor that we will consider, and next is bypass correction factor, because bypass correction factor, though it is it is not in the cross flow zone stream, sealing strip, when we are considering, it is not in cross flow zone, but whatever fluid will available in uh, what we can say uh, fluid will available in clearance, where sealing strips are available, those strips will direct the fluid towards cross flow. Okay, and that clearance will be same in the cross flow zone as it is in the window zone. Okay, so therefore I'm having two different correction factor, FB and FL, but here we are counting that we are denoting that with prime. Okay, so FB prime and FL prime. Now I'm having this ideal tube bank pressure drop, bank pressure drop that we consider over here. And as I have told you that it basically counts the frictional loss, so that will be counted, uh, that will be counted by NCV, how many rows the liquid will cross. Okay, so this is the ideal tube bank pressure drop. Okay, JF you can count from here, right? So in that way we can count delta PI, that will be corrected with FB prime and FL prime. FB prime bypass correction factor for pressure drop. This is the same expression, only we will find change in alpha value. Okay, there alpha for heat transfer coefficient alpha value were different. Here alpha values are these only. Okay, ns is the number of sealing strips, and that number of sealing strip, whatever you will fix in heat transfer coefficient, the same you will use over here. Okay, and if sealing strips are not used, you can use this FB prime from this graph depending upon the Reynolds number. Okay, so in that way you can count FB prime. Much calculations are not required because you have already checked in heat transfer coefficient whether sealing strips are required or not, and if required how many. So everything you have fixed there. Here only you need to put the values or change the value of alpha, and then you need to find out FB prime, or you can use this graph, whatever. So in that way you can find out FB correction, FB prime. FL prime will be the same expression, only I am having beta L prime instead of beta L. Okay, so that will depend on this AL by AS that we have already calculated, and ATB, ASB we have already calculated. Beta L prime you need to find from this graph and then calculate FL prime. That's it. So that is about the leakage correction factors for pressure drop. Another parameter I am having, another zone, let's say, another zone I am having is the window zone pressure drop. Okay, window zone when I am considering, you understand that is between baffle tip to shell ID. Okay, so window zone when I am considering, window zone pressure drop would be calculated by this delta PW, which is equal to FL prime to plus 0.6 NWV rho UZ square by 2. Okay, now UZ, when I am considering window zone, UZ will be the geometrical mean of UW and US. Okay, actually when we consider window zone, all these zones are what we can say connected. Effect of one zone you can study on another zone. Okay, so here I am having velocity in window zone and velocity in cross flow zone. Okay, US you have already calculated considering AS in as in Kern's method. Okay, but UW you need to find over here, that is the velocity in window zone. The velocity in window zone based on window area less the area occupied by the tubes. Okay, actually US if you consider, US is the velocity in window zone, and it will affect, it will depend on the window area minus area of tubes occupied in window zone. Okay, or in other word, if I put this W, it will depend on the flow area in window zone. Okay, so that you can calculate like this: WS shell side flow rate by density, and AW is the area, flow area in window zone. Okay, and flow area in window zone, this is in the similar line as AS is the flow area in cross flow zone at the middle. Okay, however AW is the total flow area in window zone. Okay, so how to, okay, I will see, we will discuss how to find this AW. Another parameter we have is the NW. NW is the number of tube rows available in window zone. As if I'm having NCV in cross flow zone, I'm having NWV in window zone, right? So in that way you can consider. Now we need to find out AW as well as NW. AW, when I'm considering, this is the flow area in cross flow area, sorry, this is basically flow area in window zone. Okay, and if I consider this pi ds by 4 into RA, okay, RA we have you can find from here. Okay, RA, as we have discussed, this is basically window area by total area, and if you see, this is nothing but the total area, right? And RA you can see from this graph at baffle cut. We have discussed the difference already between RA and RA prime. Okay, RA is the RA you can see as the at the baffle cut. Okay, and considering this, you can find out window area minus number of tubes or area of one tube. Okay, so how many tubes occupied the area in window zone, that you can calculate using this expression. Difference of these two will give you the area or flow area in window zone, right? And NWV, how you will calculate NWV? NCV, if you recall, NCV between the distance, that it will depend on the distance between baffle to baffle tip. Okay, and this NWV will depend on HB. HB is the what we can say, the height of bundle available in window zone. Okay, so HB by PT prime. PT prime we have discussed already, 0.87 into PT if it is triangular pitch, or PT prime will be equal to PT if it is square pitch. Okay, in that way you can find out NWV. Okay, so once I'm having this NWV and AW, we can find out UW, and we can find out pressure drop in window zone. Okay, UZ we have already seen how to find. Okay, now another zone I'm having is the end zone. Okay, end zone means where the fluid, where nozzle is available in shell and fluid is entering in the shell. Okay, so the point is, when I'm considering end zone will lie between tube sheet and the consequent baffle. Okay, tube sheet and the first baffle, you can say. Another end zone I'm having is tube sheet, that is between tube sheet and last baffle. Okay, if I consider shell, I'm having only two end zones. Okay, and when I'm considering end zone, it means there, that is the region between tube sheet and baffle, first baffle, or you can say the last baffle and tube sheet, whatever. But the baffle has only what we can say, only one baffle is there, and I'm having only one window zone. Okay, so how many tube rows, what we can say, how many tube row crossed will be available? Okay, or we can say how many restrictions will be available. Restrictions will be NCV plus NWV. Okay, because in a window zone, sorry, in baffle, I'm having only one window zone in end zone. I hope you are getting my point, what I'm trying to emphasize on. It's so total number of restrictions in cross flow zone, that will be equal to NCV plus NW. Okay, so here I'm having pressure drop in end zone, that would be equal to pressure drop, that is in ideal case. Okay, this is the same thing we have considered delta PC. Okay, but here I am having delta PE, delta PI, FB prime I am considering, because we have only the that effect of what we can say, FB or bypass. Otherwise, other effects we have already counted in delta PC. Okay, so total, if you consider delta PI, there we have multiplied with NCV. Okay, so we have divided the NCV and multiplied with NWV into, sorry, NWV plus NCV. I hope you are getting what I'm trying to emphasize on. Just a moment. Here you see delta pi I am considering, in that would be multiplied by NCV. Okay, so we will divide that and multiply by NCV plus NWV. Okay, Okay, so in that way we can have the end zone pressure drop. Now total shell side pressure drop we can consider as uh, we will consider the pressure drop in each effect and how many sorry, pressure drop in each zone and how many zones are available. Okay, so you can see total pressure drop in shell, that will be 2 into end zone, 2 into delta PE, because two end zones are available. NB minus 1 cross flow zone, because cross flow zone we are considering between two baffle tips. Okay, so number of baffles minus 1 would be the cross flow zone, plus NB is the total number of baffles, and below that we have the window zone. So window zone how many? That will be equal to number of baffles. We can consider the expression of each section, and then we can calculate delta PS. Okay, so in that way we can have pressure drop in shell side considering Bell's method, and heat transfer coefficient in shell side considering Bell's method. So you can see considering Bell's method, design is more complicated, at the same time that would be more accurate for shell side. Tube side design will remain as it is, as we have discussed before. Okay, so that is about the Bell's method, and that Bell's method is the complete example we will discuss considering Bell's method, but that will not be covered now because time is less. So I will stop this class here only. We will continue that example, Bell's method example in next class. Okay, so that's all from my side. Next class will be tomorrow 11:30 a.m. So please book the schedule the class. So that's all from my side for today. If you have any confusion, please discuss. Otherwise, that's all from my side. So thank you everyone.